Hi there everybody, this is Perry, coming to you again with another video about my Fadal. This time we're going to be talking about the spindle cooler. Let me bring you in a little bit closer so you can see this diagram better. So my Fadal was originally equipped with a spindle cooler from the factory. The spindle cooler that this particular machine that I have came with was what they called a Prestone can. And that was a colloquial name that service techs gave the cooler because really all it was just a reservoir with a pump in it, and it circulated liquid through the spindle. Now, before we talk about the mechanics of building a spindle cooler, I want to explain why you need a spindle cooler and how the spindle cooler is installed on this machine. This Fadal is from 1985, and originally they did not have an elaborate cooling system. Liquid would flow through a hose that went up through the raceway on the top of the spindle, down through a port on the bottom of the spindle, and then it would flow through the spindle housing to the top, where it would then exit and then return to the tank. Now, the reason why you would want a spindle cooler is really twofold. First, when you're actually running the spindle itself generates heat because there's friction. You can't build a frictionless spindle, so when you're running the machine, you're going to be generating, ever so little amount of heat. But as time goes on, that heat builds up, and it causes things to expand, and it causes the clearances in the bearings to get tighter, and it can cause the spindle to wear out over time. Fadal in their manual states that you can run the machine over 8,000 RPM for 5 hours continuous, but then you have to let it sit for 30 minutes as a rest. They said below 8,000 RPM you can run the spindle continuously. I think those are probably generous ratings, but anyway, what we see here is a little arrow or a origin point. And when the spindle warms up, it does two things. One, it changes the bearing clearances, which causes the spindle to change the distance between the face of the spindle and the top of the table, which is your Z height. And it also warms up the casting, which causes the casting to elongate, which is your Y distance to the column. So your Y origin and your Z origin change position as the spindle warms up, and therefore warms this casting. Now, why that's important is that on a machine like the Fadal, they do not have what's called YZ temperature compensation. On a machine like a Haas, the early Haas machines did not have a spindle cooler, but they had a thermometer, a thermistor, potentially a thermistor, that would read the temperature of the spindle housing, and they had an algorithm that would compensate for the YZ changes in dimension. Now, that algorithm had to be compensated based on calibrations they did, all the testing they did at the factory, and it got things relatively close, and those machines worked well. But on Fadal, they didn't do that. So what they added was a spindle cooler. On this particular Fadal from the factory, they had air lubricated bearings, which also cooled the spindle. On Haas's, they have air lubricated bearings. So the lube oiler reservoir, actually oil gets removed from that and then introduced into an airstream, which then lubricates the bearings. On this machine, it's been converted to a grease pack spindle. So the bearings themselves are sealed and greased, and the coolant runs through channels in the spindle nose up to the housing right here, and then it runs through the jacket, which runs around that spindle up to an O-ring seal up here and then back out. Now, my machine did not have a Prestone can when I got it, so in order to use the machine effectively and lengthen the life of the spindle, what I have done is I've acquired a number of components to build my own spindle cooler. Now, to give you some background as to why I'm doing this, let me explain what Haas did on the later, what Fadal did on the later machines. On the later machines, what they did was they had the same spindle cooler circuit, but they actually had a refrigerator that would chill the spindle. And they also had ball screws that would be chilled. So they had a ball screw here, a ball screw here, and I don't know if the x-axis ball screw was cooled, but I know that the y and the z-axis ball screws are cooled. So basically, they've got a little ball screw here, and then they have a set of seals, and then they have a circuit with some holes in the ball screw that allow fluid to be circulated through the ball screw. Now that was a problematic design because the seals would inevitably fail. My understanding of the failure mode is that while they had a filter in there was junk in the castings, in the spindle head specifically, that would then get in, fines from the cast iron would get into that liquid, they would get into the reservoir, they would not be caught by the filter, and then they would be circulated into the seal surface area where it would become a lapping compound, and the lapping compound would erode the ball screw around the seals, and then leaks would develop, and then you would get coolant in your thrust bearings, and it would blow out your thrust bearings, and your machine would get noisy, and then performance would go to heck because you've got bad thrust bearings. My machine has solid ball screws. They're not cooled or anything like that. I don't have to worry about it because they started chilling the ball screws when they got up to 400 inch per minute rapids. I've only got 300 inch per minute rapids, and the contouring feed rate goes up to 150 inches a minute. So I've only got the spindle to contend with. Now, their original design, they had a pump, they had a filter, they had a reservoir, and they had a chiller. Now, the design that came with mine was just a pump and a tank, but what I'm adding to it is I'm adding a small automatic transmission cooler radiator with a pair of fans that I can later set up to be thermostatically controlled, and then I'm adding a filter to just filter any rust and contaminants that may make their way back through that system. So let me, now that I've discussed this, let's take a look at the actual components that I acquired to build this cooler system. Now let me start with the pump. I was poking around on eBay and various places, as I have a habit of doing, and I encountered a picture of the Prestone can on a I think it was 86 or 87 Fadal. And it had starts with a G. I can't remember. It's a fairly common name. I've got one in the hard inch there. Anyway, it had a pump that looked just like this. So what I did is I went on eBay and I found a brand new 1/8 horsepower, 115 volt pump with a 3/8 NPT output that's 6 inches deep. So this pump is just a centrifugal pump, nothing exotic. I think it was $78 or so. And it has sufficient head pressure and flow for the application. Now for the filter assembly, I went to Home Depot, and they have these simple garden hose filters. They're meant for use on the intake of, say, a pressure washer. And they say on the package this is good for 450 microns, which is, just under 0.5 millimeter. It's a fairly large mesh, but for the kind of, scale that I'm expecting in this system, I think that'll be fine. I went over to the plumbing section and I picked up a 3/4 MPT and FPT, those are plumbing terms for female pipe thread, male pipe thread, but they're the fittings for garden hose. And then those were the 1/2 inch NPT. So I got 1/2 NPT to 3/8 barb fittings. Now for the radiator assembly, I have this transmission cooler. I bought this many years ago when I was going to make a TIG torch cooler that would run off of my generator welder. And I was trying to make it 12 volt, and I had prototyped it but never actually put one together. So this is just a standard, 3/8 in, 3/8 out, 2-pass, circuit. And then I've got some, looks like 5-inch muffin fans that run off of 12 volts on the other side. And then I've just got a 12 volt, it's like a laptop power supply kind of. These are the components for that. This is the top to one of the coolant tanks I got with the Fadal. It came with 2 coolant tanks. One of them had no pump in it, but it had a hose. and it had the return here. There's two returns in the bottom of the chip pan, so they had two coolant tanks. One of them looks to be, something that would have shipped with the Fadal. And then there was this made in Taiwan unit, which just so happened to be exactly the right application for this pump. So this pump right here will bolt into this location, and I welded these ears onto this so I could mount this radiator on here. And in the return circuit, I'll just mount that filter in line. This is the coolant tank that I plan to use with it. It's, I don't know, I guess it's somewhere around a 10-gallon coolant tank. I'm not going to make it smaller or change its size because I might want to use it for something else in the future. But for the time being, it holds water, or should I say it's watertight, and it's the right application for this. Now let me introduce you to what I'm going to be using as the coolant, or the fluid in this heat exchanger. Now, the original model that came with my machine used a Prestone antifreeze coolant. Now, I'm not particularly keen on using Prestone antifreeze for a couple of reasons. One of them is I'm not really keen on the disposal issues associated with ethylene glycol. The other issue is I don't want animals, even mice if it were, to come in here and find their way into the hopper and drink it and die. So what I did was I bought some RV antifreeze. This is the stuff you use in your RV for winterizing it. And what gave me the idea is, this doesn't say it on it, but it's fairly close. This is not exactly what I wanted, but they didn't have it in stock. The later machines with the chiller unit on it use Dow Frost, which is a trademark name by Dow for their antifreeze product, but it's the stuff that you put in RVs to winterize them. It's just propylene glycol with a proprietary mixture of blah 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 blah. This is basically the same stuff. It says on the side of it, propylene glycol, water, and proprietary rust and corrosion inhibitors. That sounds like exactly what I want for this job. And on top of that, it's relatively inexpensive. This stuff wasn't. This was $5 a gallon, but I've purchased similar stuff for $2 a gallon. But what was important to me is I wanted the propylene glycol mix. I didn't want the ethylene glycol or ethyl alcohol. Some of the other ones that you get for winterizing RVs have ethyl alcohol in them. And I don't want that in this application. I just want propylene glycol. This is safe for the environment. It's probably not going to tear up any of the seals inside my spindle, which was really important. I don't want to be pulling the spindle out to replace O-rings. And it's easy to obtain, and if I have a leak, it's red. I know what it is if I see red. So this is the stuff I'm going to use. I got 6 gallons of it, and I'm hoping that's going to be enough. So next I'm going to show you the assembly of the entire reservoir unit. Okay, so at this point I saved you the boredom of watching me put some screws in here. I've got the pump installed into the top of the tank, and then I secured the top of the tank to the base. Now all I have to do is just get this installed, which is just a few screws. Just need to slide that down in there. Ouch. Slide that there. Here. So I have 3 choices of hose that I can use for routing this. This one is a clear nylon reinforced. This is a black high density polyethylene. And the third is, this is just air hose. I bought some, to cut up, and this is what I got left. I'm kind of leaning towards the black polyethylene. It's a little harder to deal with initially, but I think I do that, that might be good. But I kind of like the idea of using this reinforced hose, even though it's a little stiffer at this temperature. I kind of like the idea because I can see the liquid flowing. So it's I've used this with this exact push lock fitting before, so I wouldn't have to worry about a hose clamp on that. Yeah, I think I'm going to use the clear stuff. Let me get my tools. Okay, well, our cooler unit is complete. All we have to do now is hook it up to the CNC machine. Cue hookup. Okay, now we've got the cooler unit over here. These are the two hoses that come out. I'm going to use the short one as the return because it fits better, and the long one as the feed. We got all 6 gallons of the antifreeze, the RV antifreeze in there, and we're going to turn it on and hope that there's no leaks, and we'll watch the coolant return to here, probably with some rust and other crud in there that we'll pick up, and then it'll return through that. So cross your fingers. Well, the pump's running. Sounds like it's sucking stuff up. Yep. We're starting to get some liquid back through here. And through there. That's interesting. It doesn't fill the bowl all the way. Well, I'm going to have to call it a night, guys. Battery low. Good night.